Hello there, and welcome to Sleep Science, where we explore fascinating science in a quiet, relaxing way that helps your mind unwind and drift off to sleep. Tonight, we're embarking on a thought experiment that will take us deep into the heart of physics itself. What if one of the universe's most fundamental constants, the speed of light, was just a little bit slower? Not dramatically different, not crawling along like a Sunday afternoon, but simply 10% more leisurely in its cosmic journey. It sounds like a small change, doesn't it? But as we'll discover, even the tiniest adjustment to this universal speed limit would ripple through every corner of existence. Stars would burn differently. Atoms would dance to new rhythms. Time itself would flow in strange new ways. And quite possibly, you wouldn't be here to listen to this story at all. We'll wander through a universe where light takes its time, where rainbows shift their colors, where the very atoms that make up your pillow might behave rather differently. From the nuclear furnaces of stars to the delicate chemistry of life, from the screens we stare at to the thoughts we think, everything would dance to a slightly different rhythm. So, settle in. Close your eyes if you like, and let's explore this wonderfully strange alternate reality where the universe decided to take things just a little more slowly. Picture the fastest thing you can imagine, perhaps a cheetah in full sprint, or a race car screaming down a straightaway, or even your thoughts jumping from worry to worry at 3 a.m. Now let that image drift away, and try to imagine something so much faster that your mind might simply choose to rest instead of grappling with the numbers. Light travels at 299,792,458 meters every single second. There's no need to hold on to that number, just let it float by like a cloud. It's fast enough to circle the Earth more than 7 times before you can blink. So fast that if you could somehow ride a beam of light, feeling weightless and warm, you'd reach the moon in just over a second and drift all the way to the sun in about 8 minutes. Imagine that journey, peaceful and bright, racing through the velvet darkness of space. But here's the thing, light isn't just fast, it's perfectly fast. You see, the speed of light isn't really about light at all. It's about the universe itself, about how space and time are woven together, about the very fabric of reality. Light just happens to be the messenger that carries this cosmic speed limit around for everyone to see. Think of it this way. Imagine the universe has rules, like a very elaborate game. One of the most important rules is that information, any information, can only travel so fast. No exceptions. No shortcuts. No getting around it. The speed of light is that speed limit, the universal constant that says this far, this fast, and no further. This rule governs everything. When you flip a light switch, the electricity doesn't instantly appear in the bulb. It travels along the wire at a speed related to light speed. When you send a text message, those signals bounce around at speeds that depend on this same cosmic limit. Even the forces that hold atoms together, that keep your phone from falling through your hand, they all follow this same rule. Light travels in waves, much like ripples on a pond, except these ripples move through something called the electromagnetic field. This field fills all of space, everywhere, all the time. It's invisible and weightless, but it's there, quietly humming along, ready to carry light from here to there. What makes light special is that it has no mass, zero, nothing. This means it can travel at the universe's speed limit without breaking any cosmic laws. Everything else, everything with even the tiniest bit of mass, has to travel slower, much slower, usually. The speed of light was first measured accurately by a Danish astronomer named Ole Rømer in 1676. He was studying Jupiter's moons, timing their eclipses, when he noticed something odd. The The eclipses seemed to happen at slightly different times depending on where Earth was in its orbit. Roma realized this wasn't because the moons were misbehaving, it was because light from Jupiter took longer to reach Earth when we were farther away. By measuring these tiny delays, he calculated light's speed. Not perfectly, but close enough to astonish everyone and prove that light didn't travel instantly. Later, scientists got more clever. They bounced light between mirrors, measured laser pulses, and eventually defined the meter itself based on how far light travels in a specific fraction of a second. The speed of light became so precisely known that we use it to define distance rather than the other way around. But why does light travel at this particular speed? That's a deeper question, one that touches the very heart of physics. The speed of light emerges from two other properties of empty space, something called the electric permittivity and magnetic permeability. These describe how easily electric and magnetic fields can exist in a vacuum. When you do the math, and it's surprisingly simple math, you get the speed of light. It's as if the universe looked at these two properties of space and said, right, if electric and magnetic fields are going to exist, then light will travel at exactly this speed. No negotiation, no compromise. This speed or nothing. This speed also connects to Einstein's famous equation, E equals mc squared. The c in that equation is the speed of light, and it appears there because it represents the conversion rate between mass and energy. It's the cosmic exchange rate, if you will, telling us how much energy is locked away inside every bit of matter. So when we talk about the speed of light, we're really talking about the speed of causality, the pace at which cause and effect can ripple through the universe. It's the speed of information, the rate at which the universe can change and respond to change. And in our universe, right now, this speed has a very specific value. Light races along at its particular pace, carrying energy and information, connecting distant parts of the cosmos, making chemistry possible, powering the stars, and allowing you to see these words. But what if it didn't? What if this fundamental constant, this cosmic speed limit, was just a little bit different? What if light decided to slow down just a touch? Einstein had a habit of taking things everyone thought they understood and politely suggesting they might want to think again. Take time, for instance. Before Einstein, time was simple. It flowed like a river, the same for everyone, everywhere. 1 second on Earth was 1 second on Mars. 1 second in a speeding train, 1 second floating in the depths of space. Time was time, reliable and steady, like a cosmic metronome keeping the universe in rhythm. But Einstein noticed something troubling about light. No matter how fast you moved toward it or away from it, light always seemed to travel at the same speed. This was deeply weird. If you're in a car driving toward another car, the two cars approach each other faster than if one car was sitting still. But light doesn't behave like cars. Light travels at the same speed whether you're running toward it, away from it, or doing cartwheels. This led Einstein to a remarkable conclusion. The speed of light isn't just fast, it's absolute. It's the same for everyone, everywhere, always. And if that's true, then something else had to give. That something was time itself. Einstein realized that time isn't a river flowing at the same rate for everyone. It's more like a stretchy fabric that can speed up and slow down depending on how fast you're moving and how close you are to massive objects. The speed of light became the cosmic constant that holds this strange, flexible reality together. Here's where it gets wonderfully strange. The speed of light isn't really about light. It's about the universe's fundamental speed limit, the fastest that anything at all, can travel through space. Information can't go faster, energy can't go faster. Cause and effect can't happen faster. The speed of light is the speed of reality itself. This speed limit shows up everywhere in physics, often in places that have nothing obvious to do with light. It appears in equations about gravity, about the forces inside atoms, about the expansion of the universe. It's woven into the very mathematics of existence. Why does this speed limit exist? Think of space and time as a single thing, space-time, like a vast fabric stretching through the cosmos. This fabric has properties just like any material. Silk feels different from wool, water behaves differently from honey. Space-time has its own texture, its own rules about how things can move through it. The speed of light emerges from these properties of space-time. It's not arbitrary, not something the universe picked out of a hat. It's a consequence of how space and time are put together at the deepest level. Change those fundamental properties and you change the speed of light. Change the speed of light and you change everything. This speed limit also creates some of the universe's most mind-bending effects. Time dilation, for instance. Travel fast enough, close enough to light speed, and time slows down for you compared to everyone else. It's not just that clocks run slowly, time itself actually passes more slowly. You age more slowly, chemical reactions happen more slowly, thoughts think more slowly. Length contraction works the same way. Objects get shorter in the direction they're traveling as they approach light speed. Again, this isn't just measurement error or optical illusion. The objects actually become shorter, squeezed by the geometry of space-time itself. And then there's E equals m squared, perhaps the most famous equation in all of science. That little c represents the speed of light, and it appears squared, multiplied by itself. This tells us that even tiny amounts of matter contain enormous amounts of energy. The speed of light is the conversion factor, the cosmic exchange rate between matter and energy. All of this happens because the speed of light is absolute, unchanging, the same for everyone everywhere. It's the universe's way of saying, this is as fast as anything can possibly go, and if you want to understand how reality works, you need to respect this limit. But what makes this speed limit so special? Why this particular number and not some other one? The answer lies in the deep structure of space itself. Empty space isn't actually empty. It's filled with fields, invisible things that carry forces and energy. The electromagnetic field, for instance, fills all of space and carries light waves. These fields have properties, much like how water has properties that determine how waves move across its surface. The speed of light emerges from these field properties. It's determined by how electric and magnetic effects ripple through the vacuum of space. Change those underlying properties, and you change light's speed. Make the electromagnetic field a bit more resistant to change, a bit more stubborn, and light slows down. Make it more responsive, more eager to carry waves, and light speeds up. This connection runs deep. The speed of light doesn't just affect light. It affects everything that depends on electromagnetic forces, which turns out to be almost everything. The forces that hold atoms together, the chemistry that powers life, the nuclear reactions that light the stars, they all depend on electromagnetic interactions. They all dance to the rhythm set by light speed. So, when we ask, what would happen if light were 10% slower, we're really asking, what would happen if one of the universe's most fundamental properties changed? We're imagining a cosmos with different rules, different possibilities, different limits. It's like asking what would happen if gravity were weaker, or if atoms were larger, or if time flowed backwards. These aren't just technical questions for physicists to ponder over coffee. They're windows into understanding why our universe is the way it is, why it works so well for stars and planets, and, eventually, for life itself. The speed of light is the universe's way of connecting space and time, matter and energy, cause and effect. It's the cosmic speed limit that makes everything else possible. And in our universe, it has exactly the value it needs to create a cosmos rich enough for complexity, stable enough for chemistry, and interesting enough for minds to evolve that can wonder about such things. But what if it didn't? Imagine if you could reach into the universe's control panel and find a dial labeled fundamental constants, and right there, next to settings for gravity and quantum mechanics, you spot the speed of light. What if you gave that dial just the gentlest turn? Not a dramatic twist, not a complete reimagining of physics, but just a small adjustment, 10% slower. Instead of light racing along at 299 million meters per second, it now cruises at a more leisurely 269 million meters per second. It doesn't sound like much, does it? After all, 269 million meters per second is still breathtakingly fast. Light would still circle the Earth 6.5 times every second instead of 7.5. It would still reach the Moon in just over a second, still travel from the Sun to Earth in about 9 minutes instead of 8. But here's the thing about fundamental constants. They're fundamental for a reason. They're woven into the very fabric of reality so deeply that changing one is like pulling a thread from a sweater. Everything connected to that thread starts to unravel, shift, and reorganize itself into new patterns. The speed of light isn't just about how fast light travels. It's about how fast information can move through the universe, how quickly cause and effect can ripple from one place to another. It's the cosmic speed limit that governs everything from the forces inside atoms to the expansion of space itself. So when we slow light down by 10%, we're not just making photons a bit more relaxed in their journey across the cosmos. We're changing one of the universe's most basic rules, and that change cascades through every corner of physics like ripples spreading across a quiet pond. Let's start with something simple: energy. Einstein's famous equation, E equals mc squared, tells us that mass and energy are two sides of the same coin. The speed of light, that c in the equation, is the conversion rate between them. Slow down light, and you change how much energy is locked away inside every particle of matter. In our 10% slower universe, E would equal mc times a smaller number squared. This means every atom, every molecule, every particle would contain less energy than in our familiar cosmos. Not dramatically less, but noticeably less. About 19% less, to be precise. This might sound like good news. Less energy means less explosive potential, right? But energy is also what powers everything from chemical reactions to nuclear fusion. It's what makes stars shine, what drives the chemistry of life, what holds the universe together and powers its constant dance of change. With less energy available, everything would have to work a bit harder to make things happen. Chemical reactions would need different conditions to get started. Nuclear fusion in stars would proceed at different rates. The very atoms that make up your body would behave differently, bound together by forces that depend on electromagnetic energy. But the changes go deeper than energy. The speed of light is also intimately connected to something called the fine structure constant, a number that governs how electromagnetic forces work. This constant determines how tightly electrons are bound to atomic nuclei, how atoms absorb and emit light, how molecules form and break apart. Slow down light, and you change this constant. Atoms would have different energy levels. Electrons would orbit their nuclei in slightly different ways. The periodic table might look familiar, but the elements would behave differently. Hydrogen would still be hydrogen, carbon would still be carbon, but their personalities, their chemical quirks and preferences would shift. This affects everything that depends on chemistry, which is essentially everything. The way proteins fold, the strength of chemical bonds, the colors that different elements emit when heated, the very basis of biochemistry, all of it would dance to a new rhythm. And then there's time itself. In Einstein's universe, time is connected to space through the speed of light. Slow down light, and you change how time and space relate to each other. Time dilation effects would work differently. The universe's clock would tick to a subtly different beat. Gravity would feel these changes too. Einstein's general relativity describes gravity not as a force, but as the curvature of space-time, and the equations that govern this curvature depend on the speed of light. Change light speed, and you change how mass and energy warp the fabric of space and time. This doesn't mean gravity would be stronger or weaker, exactly. It means the relationship between matter, energy, space, and time would be different. Black holes would form under different conditions. The expansion of the universe would follow a different timeline. Gravitational waves would ripple through space at a different speed. Even seemingly distant phenomena would feel the effects. The cosmic microwave background, that faint afterglow of the Big Bang that fills all of space, would have different properties. The formation of galaxies and stars would follow altered patterns. The very history of the universe would unfold differently. Perhaps, most remarkably, all of these changes would be connected. You can't just slow down light and leave everything else unchanged. The universe is too interconnected for that. Change the speed of light, and you change the fine structure constant. Change that, and you alter atomic behavior. Change atomic behavior, and chemistry shifts. Change chemistry, and stars burn differently. Change stellar physics, and planetary formation follows new rules. It's like a cosmic domino effect, but instead of pieces falling in sequence, everything adjusts simultaneously to accommodate the new reality. The universe would reorganize itself around this new speed limit, finding new equilibriums, new stable configurations, new ways for complexity to emerge. And here's the most remarkable part. This new universe might work just fine. It would be different, certainly. But the laws of physics would still be consistent, still allow for structure and complexity, still permit the dance of matter and energy that makes interesting things possible. The question is, would this different universe be hospitable to life? Would stars still shine brightly enough and long enough to warm planets? Would chemistry still be rich enough to build complex molecules? Would time flow in a way that allows for growth and change, and the slow accumulation of complexity that seems necessary for consciousness to emerge? We're about to find out. Deep inside every atom, electrons are performing an intricate ballet, spinning and orbiting in patterns so precise they make Swiss clockwork look casual. These electrons don't just randomly buzz around their atomic nuclei like confused bees. They occupy specific energy levels, specific distances, specific patterns that are determined by the fundamental forces of nature. And one of the most important numbers governing this atomic choreography is something called the fine structure constant. The fine structure constant is a peculiar number, about 1/137. It seems random, almost arbitrary, but it's actually one of the most important numbers in the universe. It determines how strongly electromagnetic forces work, how tightly electrons are bound to their nuclei, how atoms absorb and emit light. This constant depends on the speed of light. Change light speed and you change this number. And when you change how electromagnetic forces work at the atomic level, you change everything. In our 10% slower universe, the fine structure constant would be different. Not dramatically different, but enough to shift the entire atomic world into new patterns. Electrons would orbit their nuclei a bit differently. Energy levels would shift. The very architecture of atoms would be subtly but importantly altered. Think of an atom like a tiny musical instrument. The electrons are like strings, vibrating at specific frequencies, creating specific notes. The fine structure constant is like the tension in those strings. Change the tension and all the notes shift. The atom plays a different song. This new atomic music would affect everything. Take hydrogen, the simplest atom, with just one proton and one electron. In our familiar universe, hydrogen absorbs and emits light at very specific wavelengths, creating distinctive lines in the spectrum. These lines are like hydrogen's signature, its way of announcing its presence in stars and gas clouds across the cosmos. But in our slower light universe, hydrogen's signature would change. The electron would orbit at a slightly different distance from the proton. It would absorb and emit light at different wavelengths. Hydrogen would still be hydrogen, but it would have a different personality, a different set of preferences and behaviors. The same would be true for every element. Carbon, the backbone of life as we know it, would form bonds differently. The electrons that carbon shares with other atoms to create molecules would be held with different strengths at different angles, creating different molecular shapes. This matters enormously for chemistry. The shape of a molecule determines how it behaves, how it interacts with other molecules, whether it can perform the complex chemical reactions that life depends on. Change the shapes and you change the chemistry. Change the chemistry and you might change whether life is possible at all. Let's think about water for a moment. Water's remarkable properties, its ability to dissolve so many different substances, its expansion when it freezes, its perfect temperature range for remaining liquid on Earth, all of these depend on water's molecular shape. The water molecule is bent, like a boomerang, with the oxygen atom at the center and hydrogen atoms at the tips. This shape comes from how electrons are shared between the oxygen and hydrogen atoms, how they form what chemists call covalent bonds. In our slower light universe, these bonds might form at different angles with different strengths. Water might have a slightly different shape, different properties, different behaviors. Would it still be wet? Would it still freeze and boil at convenient temperatures? Would it still be able to dissolve the countless substances that make biochemistry possible? These aren't questions we can answer without doing the detailed calculations, but they hint at how even small changes in fundamental constants can ripple through to affect the most basic substances we depend on. The colors of things would change too. When atoms absorb light, electrons jump from one energy level to another. When they fall back down, they emit light at specific wavelengths, creating the colors we see. Change the energy levels, and you change the colors. A red rose might be purple in our new universe. Copper might gleam blue instead of its familiar orange. The sun itself, if it could still form and shine in this altered cosmos, might bathe everything in a different hue. But perhaps the most important changes would be in the realm of complex chemistry. Life depends on enormous molecules, proteins, and DNA that fold into intricate three-dimensional shapes. These shapes are held together by countless weak bonds, electromagnetic forces operating between different parts of the molecule. Change the fine structure constant and you change these forces. Proteins might fold differently or not at all. DNA might not be stable enough to store genetic information reliably. The chemical networks that power living cells might collapse or reorganize into completely different patterns. This doesn't necessarily mean life would be impossible. It might mean life would be different, based on different chemistry, using different molecules, following different rules. But it might also mean that the delicate balance of forces that makes complex chemistry possible would be disrupted, making any kind of life impossible. There's also the question of stability. In our universe, atoms are remarkably stable. Once formed, They can last billions of years without decaying or changing. This stability depends on the precise balance of forces inside the nucleus and the energy levels of electrons. Change the fundamental constants, and some atoms might become unstable. Elements that are long-lived in our universe might decay quickly in the new one. Conversely, some combinations that are impossible in our universe might become stable, creating new elements with new properties. The periodic table itself might look different, not just in the details of how elements behave, but in which elements can exist at all. The universe might be richer in some elements and poorer in others, creating a completely different palette for chemistry to work with. And all of this traces back to that simple change, slowing light down by 10%. Such a small adjustment to such a fundamental constant, but it propagates through the laws of physics like a wave, changing the rules that govern matter at its most basic level. The electrons in every atom would feel the change, adjusting their orbits and energy levels to accommodate the new reality. Chemistry would reorganize itself around these new atomic personalities. And from there, the effects would continue to ripple outward, touching everything that depends on atoms and molecules and the forces that bind them together. Which is to say, everything. Color, as it turns out, is just light showing off, waves of electromagnetic energy painted across a spectrum that stretches from radio whispers to gamma-ray shouts. Close your eyes for a moment and picture the world you know, the warm yellow of morning sunlight streaming through your window, the deep blue of a summer sky, the gentle green of leaves rustling in a breeze. Now let those familiar colors soften and drift away, because in our 10% slower universe, this entire palette would be transformed. Imagine waking up in a world bathed in permanent, soft, rose gold light, like a sunset that never quite ends. The sun would hang in the sky with a deeper, warmer glow, painting everything in honeyed tones. Shadows would be softer, gentler, the edges of things less sharp and more forgiving. Don't worry about understanding exactly why this happens, just let yourself feel what this golden world might be like. Your morning coffee might steam in shades that have no name, vapor-catching light that doesn't exist in our universe. The sky might stretch overhead in hues of amber and copper, with clouds that drift like brushstrokes of cream against a canvas of perpetual evening warmth. There's something deeply peaceful about imagining such a world where everything glows as if lit by candlelight. But the changes would ripple deeper than just the colors your eyes can see. Let your mind wander gently through the invisible parts of light, the radio waves that carry whispered messages, the infrared that feels like warmth on your skin on a cold day. All of these would shift to new frequencies, new energies, creating an electromagnetic symphony played in an entirely different key. Plants, if they existed in this slower light world, might need to paint themselves in completely different colors to catch the altered sunlight. Instead of the familiar green of chlorophyll, perhaps they would dress themselves in deep purples or rich burgundies, creating forests that glow like wine in the golden light. Don't try to follow all the science. Just drift through these imagined landscapes, letting the colors wash over you like a gentle tide. The very concept of a rainbow would be rewritten. Instead of red through violet, there might be an entirely different arc of hues stretching across the sky after rain, wavelengths that paint the world in colors you've never seen because they simply don't exist in our universe. Imagine standing in such a rain, feeling the warm droplets while above you, a bridge of impossible colors stretches from horizon to horizon. Rest your mind here for a moment. Let yourself simply exist in this imagined world of altered light, where everything glows with unfamiliar beauty, where the very air seems to shimmer with new possibilities. There's no need to understand the technical details, just breathe in the peace of a universe that chose to paint itself in different shades. But let's think about our eyes for a moment. They evolved to detect the light that our sun produces most abundantly, the light that penetrates our atmosphere most efficiently, the light that provides the most useful information about our environment. In a universe where the electromagnetic spectrum was shifted, eyes would evolve differently. Maybe vision would be sensitive to what we now call infrared, seeing heat signatures as readily as we see colors. Maybe eyes would detect ultraviolet patterns invisible to us, revealing hidden information about the world. Or maybe the very concept of color vision wouldn't develop at all if the useful part of the spectrum was too narrow or too energy poor to provide rich visual information. Radio waves would be affected too. These long wavelength, low energy waves carry our radio broadcasts, our cell phone signals, our Wi-Fi networks. In our altered universe, the radio spectrum would shift, potentially making our current communication technologies useless. But more fundamentally, radio astronomy would reveal a different cosmos. Radio telescopes detect electromagnetic radiation from space, mapping distant galaxies, neutron stars, and black holes by the radio waves they emit. Change the electromagnetic spectrum, and you change what radio astronomy can observe. The cosmic microwave background, that faint afterglow of the Big Bang that fills all of space, might no longer be in the microwave range at all. It might shift to longer wavelengths, becoming a cosmic radio background, or to shorter ones, becoming something else entirely. Our understanding of the early universe, based on detailed observations of this background radiation, would have to be completely reconsidered. At the high energy end of the spectrum, things get even more dramatic. X-rays and gamma rays carry enormous amounts of energy, enough to penetrate matter, ionize atoms, and power the most violent events in the universe. In our slower light cosmos, these high-energy phenomena would be shifted to different frequencies, carrying different amounts of energy. Medical X-rays might not work the way they do now. The energy needed to penetrate human tissue and create useful images would correspond to different frequencies, requiring different technology, different safety considerations. Or maybe the energy requirements would be so different that X-ray imaging wouldn't be practical at all. Gamma-ray bursts, the most energetic events known in the universe, might shift into a completely different part of the spectrum. Instead of gamma rays, they might emit what we currently think of as X-rays or ultraviolet or even visible light. Astronomers studying these cosmic fireworks would be looking in entirely the wrong part of the spectrum. But perhaps the most profound change would be in the energy budget of the universe itself. Every photon would carry a different amount of energy. Every electromagnetic process, from the fusion in stellar cores to the chemical reactions in living cells, would operate with a different energy currency. Photosynthesis, the process that converts sunlight into chemical energy and powers most life on Earth, depends critically on the energy carried by visible light photons. These photons need to carry just enough energy to drive the chemical reactions in chlorophyll, but not so much energy that they damage the delicate molecular machinery. In our slower light universe, this energy balance would be completely different. Plants, if they could exist at all, might need to use different wavelengths of light, different chemical processes, different molecular machinery entirely. The green world we know might be replaced by something utterly alien. Even more basically, the very concept of temperature would be affected. Temperature is related to the average energy of particles, and much of that energy transfer happens through electromagnetic radiation. Objects emit thermal radiation based on their temperature, creating the infrared glow we can detect with thermal cameras. Change the electromagnetic spectrum, and you change how thermal radiation works, how heat transfers from one object to another, how temperature and electromagnetic energy relate to each other. The universe might be a fundamentally colder place, or a fundamentally hotter one, or just fundamentally different in ways that are hard to imagine. So when we slow down light by 10%, we're not just changing how fast photons travel. We're shifting the entire electromagnetic rainbow, repainting the universe in frequencies and colors and energies that might be beautiful or strange, or completely invisible to eyes that evolved for a different kind of light. The cosmos would still shine, but it would shine in a different song. Every star in the sky is essentially a massive nuclear reactor, fusing hydrogen into helium with all the patience of a cosmic chef preparing the universe's most elaborate meal. But in our 10% slower universe, the recipes would change. The stellar kitchens would operate under different rules, cooking up elements at different rates, shining with different intensities, living for different spans of time. Some stars might burn brighter, others dimmer. Some might live longer, others shorter. The entire stellar life cycle would dance to a new rhythm. To understand why, we need to peek inside a star's core, where temperatures reach millions of degrees and pressure crushes matter into densities that make lead feel light as air. Here, hydrogen nuclei, each carrying a positive electric charge, are pressed so closely together they overcome their natural tendency to repel each other and fuse into helium. This fusion process releases energy according to Einstein's E equals mc squared. The tiny amount of mass lost when hydrogen becomes helium gets converted into a tremendous amount of energy. This energy works its way slowly outward through the star, eventually escaping as the light and heat that warm planets and make life possible. But in our slower light universe, that crucial equation changes. With C 10% smaller, the energy released by each fusion reaction would be about 19% less. That might sound like a small reduction, but it would have enormous consequences for how stars work. Less energy per fusion means stars would need to fuse hydrogen faster to maintain the same brightness, or they would burn dimmer, radiating less light and heat into space. Either way, the delicate balance that keeps stars stable would be disrupted. You see, stars exist in a constant tug of war between gravity trying to crush them inward and radiation pressure pushing outward. Gravity wants to collapse the star into a tiny, dense ball. The energy from fusion creates radiation that pushes back, keeping the star inflated like a cosmic balloon. With less energy per fusion reaction, this balance would shift. Stars might contract slightly, increasing the temperature and pressure in their cores until fusion rates increased enough to restore equilibrium. Or they might simply accept burning dimmer, settling into a new, cooler equilibrium. The color of stars would change too. A star's color depends on its surface temperature, which in turn depends on how much energy is flowing outward from the core. Less energy means cooler surfaces, which means redder light. Our yellow sun might become distinctly orange or even red. But the changes would go much deeper than color. The main sequence, the stable phase of stellar life when stars steadily fuse hydrogen in their cores, would be affected. Stars might spend longer in this phase because they're using their nuclear fuel more slowly, burning dimmer but lasting longer. Or they might spend less time because the altered physics changes how efficiently they can extract energy from their fuel. Massive stars, the giants that live fast and die young in our universe, might behave very differently. These stars burn through their nuclear fuel quickly, fusing heavier and heavier elements in their cores until they create iron. Iron can't be fused for energy, so the core collapses catastrophically, triggering a supernova explosion. With altered fusion energy, this entire process would change. Maybe massive stars would burn more slowly, living longer before reaching the iron crisis. Maybe they would burn faster, reaching their explosive end more quickly. Maybe the balance of forces would be so different that some massive stars wouldn't explode at all, instead collapsing directly into black holes. Supernovae are crucial for the universe because they're the primary source of elements heavier than iron. Gold, silver, platinum, uranium, all the heavy elements are forged in these stellar explosions and scattered into space to be incorporated into new stars, planets, and potentially living beings. Change the supernova process, and you change the chemical evolution of the universe. Maybe our slower light cosmos would be richer in some elements and poorer in others. Maybe the heavy elements essential for rocky planets and complex chemistry would be much rarer, making Earth-like worlds uncommon. White dwarf stars, the hot, dense remnants of stars like our Sun, would also be affected. These stellar corpses shine by slowly radiating away their stored heat, cooling and fading over billions of years. With different electromagnetic properties, they might cool faster or slower, changing how long they remain visible. Neutron stars, even denser remnants of more massive stars, would feel the changes too. These objects are so dense that a teaspoon of neutron star material would weigh as much as a mountain. Their structure depends on the balance between gravity and the fundamental forces that prevent matter from collapsing completely. Change the fundamental constants, and you might change what kinds of neutron stars can exist, how massive they can be before collapsing into black holes, how they spin and pulse and emit radiation into space. Black holes themselves would be affected in subtle ways. While gravity would still work the same way, the relationship between mass and energy would be different. Black holes form when matter becomes so dense that not even light can escape. But if light travels slower, does that change the conditions needed for black hole formation? The answer isn't simple, because it's not just about light escaping, it's about the fundamental relationship between space, time, mass, and energy. Black holes would still form, but the exact conditions and properties might be different. Perhaps most importantly for life, the habitable zones around stars would shift. This is the region where planets can maintain liquid water on their surfaces, not too hot and not too cold. With stars burning dimmer in our slower light universe, these zones would be closer to the stars. Earth might find itself outside the habitable zone, too cold for liquid water, or maybe the reduced stellar output would be perfectly compensated by other changes in atmospheric or planetary physics. The delicate balance that makes our world livable might tip in either direction. Binary star systems, where two stars orbit each other, would face their own challenges. Sometimes matter flows from one star to its companion, creating dramatic fireworks as material spirals inward and heats up. These processes depend on electromagnetic radiation to carry away energy and angular momentum. With altered radiation properties, binary interactions might be more violent or more gentle, changing the population of exotic objects like X-ray binaries, cataclysmic variables, and Type Ia supernovae. These objects serve as cosmic lighthouses, helping astronomers measure distances and understand the expansion of the universe. So our slower light cosmos would be filled with stars singing new songs, burning with different rhythms, living different lives, and creating different legacies of elements and energy. The night sky might be dimmer overall, painted in redder hues, populated by different types of stellar objects. But it would still be beautiful, still be dynamic, still be the stage on which the drama of cosmic evolution unfolds. Just a different drama with different characters, different plot twists, and perhaps different endings. If you thought time was already a bit of a troublemaker in Einstein's universe, wait until you see what happens when light decides to take its time. Time, as Einstein showed us, isn't the steady, reliable constant we once believed it to be. It stretches and compresses, speeds up and slows down, depending on how fast you're moving, and how deep you are in a gravitational field. The speed of light is woven into every equation that describes these temporal acrobatics. Change the speed of light, and you change how time itself behaves throughout the universe. Let's start with time dilation, that wonderfully weird effect where time passes differently for different observers. In our familiar universe, if you travel at high speeds approaching light speed, time slows down for you relative to everyone else. This isn't just theory anymore. We've seen it happen with particles in accelerators, with atomic clocks on airplanes, with GPS satellites orbiting Earth. But in our 10% slower universe, the mathematics of time dilation would shift. The critical speeds at which time effects become noticeable would be lower. What we now consider moderate speeds might produce dramatic time warping effects. Imagine traveling in a car at highway speeds. In our current universe, you'd experience time dilation so tiny, it's essentially unmeasurable. But in the slower light cosmos, even relatively modest speeds might produce detectable effects. Not dramatic time warping, but perhaps enough to require adjustments in precision timekeeping. This might sound like a minor technical detail, but consider how much our modern world depends on precise time coordination. GPS satellites, financial transactions, power grids, telecommunications, internet synchronization, all of these systems rely on incredibly accurate timing. If everyday motions produced measurable time effects, our technology would need to be fundamentally redesigned. But the changes would go much deeper than technology. The relationship between space and time, what physicists call space-time, would be different. Einstein's equations describe how mass and energy curve this space-time fabric, creating what we experience as gravity. These equations have the speed of light built into them, not just once, but multiple times. Change light speed, and you change how matter warps space-time, how gravitational waves propagate, how the universe expands, how black holes form and behave. Gravitational time dilation would also be affected. This is the effect where time passes more slowly in stronger gravitational fields, closer to massive objects. On Earth, your head ages slightly faster than your feet because it's farther from Earth's center, experiencing slightly weaker gravity. With a different speed of light, this effect would scale differently. Maybe gravitational time differences would be more pronounced, making it easier to detect with simple experiments. Or maybe they'd be reduced, requiring even more sensitive instruments to observe. The expansion of the universe itself would follow different rules. Einstein's equations of general relativity, which describe how the universe grows and evolves, would give different answers with a different light speed. The cosmos might expand faster or slower, age at a different rate, reach different final states. This could affect the cosmic timeline in profound ways. In our universe, it took about 13.8 billion years for conditions to evolve from the Big Bang to the formation of galaxies, stars, and eventually planets capable of supporting life. Change the fundamental constants, and this timeline might be completely different. Maybe our slower light universe would evolve more quickly, reaching similar complexity in less time. Maybe it would evolve more slowly, requiring tens of billions of years to develop interesting structures. Maybe the expansion rate would be so different that galaxies never form at all, or form in completely different patterns. Black holes, those regions of space-time where gravity is so strong that nothing can escape, would also behave differently. The event horizon, the boundary beyond which nothing can return, is defined in terms of the speed of light. Change light speed, and you change where that boundary sits. This doesn't necessarily mean black holes would be bigger or smaller. The relationship is more subtle, involving how mass, energy, and space-time curvature relate to each other. But it might mean that black holes form under different conditions, or that the process of falling into one feels different to an outside observer. Gravitational waves, ripples in space-time itself, travel at the speed of light. In our slower universe, these waves would propagate more slowly, carrying information about cosmic events at a more leisurely pace. The gravitational wave detectors that have opened a new window on the universe would need to be recalibrated for different wave speeds and frequencies. But perhaps the most mind-bending change would be in the fundamental nature of simultaneity, the question of what it means for events to happen at the same time. In Einstein's relativity, simultaneity is relative. Events that appear simultaneous to one observer might not be simultaneous to another observer moving at a different speed. This effect depends critically on the speed of light. Change that speed, and you change how simultaneity works, how cause and effect propagate through the universe, how information can flow from one place to another. In extreme cases, the changes might be dramatic enough to alter the very concept of causality. In our universe, cause must precede effect, at least for any observer. But the mathematical relationships that ensure this depend on the speed of light being exactly what it is. Change light speed significantly, and you might create situations where some observers see effects preceding their causes, violating our basic understanding of how the universe operates. This probably wouldn't happen with just a 10% change, but it hints at how fundamental the speed of light is to the logical structure of reality. Time zones would take on new meaning too. Currently, we can synchronize clocks across the globe with incredible precision, accounting for the tiny delays as signals travel at light speed. With a slower light speed, these delays would be longer, making global synchronization more challenging. But more fundamentally, the very nature of time as we experience it, the flow from past to future, the accumulation of moments into memories, the unfolding of events in sequence, all of this emerges from the deep structure of space-time as described by Einstein's equations. Change the speed of light, and you change that deep structure. Time would still flow, events would still unfold in sequence, but the mathematical relationships governing these processes would be different. Time might feel different in ways that are hard to imagine, like trying to describe color to someone who has never seen. In our slower light universe, time would still be time, but it would be a different kind of time, governed by different rules, flowing according to different mathematics, connecting space and matter and energy in subtly but importantly different ways. And all of this from just a 10% adjustment to a single cosmic constant. Time, it turns out, is even more delicate and interconnected than we might have imagined. Chemistry is essentially the art of atoms getting to know each other. Sometimes they're just friends, sometimes they form lasting bonds, and occasionally they have explosive breakups. But in our 10% slower universe, these atomic relationships would follow different rules. Don't worry about memorizing the science. Just let yourself drift into imagining a world where the very molecules around you behave like different personalities, with new preferences and quirks. Think about water for a moment, that most familiar of substances. Feel it in your mind, cool and flowing, the way it moves over your skin in a shower, the way it steams from your morning tea. In our slower light world, water might feel different against your fingertips, perhaps thicker, more like silk than simple liquid. Maybe it would bead on surfaces differently, or flow with a new kind of grace that your body could somehow sense even before your mind understood why. There's something peaceful about imagining such changes. Let your thoughts drift to salt, that simple combination of sodium and chlorine that makes the ocean taste of tears and memories. In our altered universe, salt crystals might grow into new shapes, perhaps more delicate, more intricate, like tiny architectural wonders scattered across the bottom of tide pools that shimmer with unfamiliar light. The very air you breathe might carry a different feeling. Nothing harmful, just different, like the way air feels different at the ocean versus the mountains. The oxygen molecules dancing in your lungs might pair with your blood in subtly new ways, perhaps making each breath feel deeper, more satisfying, as if the universe had learned to be a little more generous with the gift of breathing. Rest here for a moment and imagine the chemistry of cooking in such a world. Perhaps bread would rise differently, or sugar would caramelize at different temperatures, filling your kitchen with aromas that have no names. Maybe the Maillard reaction that browns your morning toast would paint it in new shades, creating flavors that would make your taste buds wonder at the creativity of this altered chemistry. Don't try to follow the technical details about electron sharing and molecular bonds. Just let yourself feel what it might be like to live in a world where every chemical interaction had been gently tuned to a slightly different key. Where your morning coffee might brew into colors we don't have words for, and the steam rising from your cup might carry molecular songs that somehow taste like peace. The proteins in your body might fold differently, but in your imagination, let this feel like a good thing. Perhaps they'd be more stable, more resilient, making you feel stronger in some quiet, deep way. Maybe the chemistry of digestion would be more efficient, leaving you feeling lighter, more energetic, as if your body had learned a more elegant dance with the food you eat. There's no need to understand exactly how chemical bonds would change. Just picture molecules as tiny dancers, learning new choreographies, finding new ways to create the substances that make life possible. Carbon might still be the backbone of life, but perhaps it would build molecular sculptures that are even more beautiful, even more perfectly suited to housing consciousness and dreams. Even the chemistry of emotions might be different. The neurotransmitters that carry feelings through your brain might work more smoothly, more gently. Perhaps joy would feel more buoyant, sadness would be easier to process, and love would taste even sweeter on the molecular level. Let that thought settle into your mind like a warm blanket, the idea that chemistry itself might become more kind. Close your eyes and just breathe for a moment, feeling grateful for the chemical symphony happening inside you right now. Even as you imagine how beautifully it might play in a universe that chose to slow down light just enough to make everything a little more gentle, a little more forgiving, a little more designed for peace. Now consider water, perhaps the most important molecule for life as we know it. Water's remarkable properties come from its bent molecular shape and the way its electrons are distributed. The oxygen atom hogs the electrons a bit, creating a slightly negative end of the molecule and a slightly positive end where the hydrogen atoms sit. This polarity allows water molecules to form hydrogen bonds with each other, weak attractions that give water its unique characteristics. Water expands when it freezes, has unusually high boiling and melting points for such a small molecule, and can dissolve an extraordinary variety of substances. In our altered universe, the electron distribution in water might be different. Maybe the oxygen would be more or less greedy for electrons, changing the molecule's polarity. Maybe the hydrogen bonds would be stronger or weaker, fundamentally altering water's behavior. Stronger hydrogen bonds might make water more viscous, thicker, slower to flow. It might have higher boiling and freezing points, existing as a solid or gas under conditions where we expect liquid. Weaker hydrogen bonds might make water more volatile, quicker to evaporate, less able to dissolve other substances. Either way, the implications for life would be enormous. Life as we know it is essentially aqueous chemistry, reactions happening in water solutions. Change water's properties, and you change the entire chemical environment in which life operates. But let's think about carbon, the element that forms the backbone of all known life. Carbon is special because it can form four strong bonds with other atoms, allowing it to create complex, branching molecular structures. These structures can be chains, rings, networks, three-dimensional frameworks of almost unlimited variety. In our slower light universe, carbon's bonding preferences might shift. Maybe it would still form four bonds, but at different angles, creating molecules with different shapes. Maybe it would prefer to form three strong bonds and one weak one, or two very strong bonds, fundamentally changing the kinds of structures it could create. This would affect every carbon-based molecule, from simple methane to complex proteins. Methane might have a different shape, making it a less effective greenhouse gas or a more effective one. Plastics might be impossible to create or might form naturally without human intervention. Proteins, the molecular machines that drive most biological processes, might not be able to fold into their characteristic three-dimensional shapes. These shapes are crucial for protein function, determined by countless weak interactions between different parts of the molecule. Change the strength of these interactions, and proteins might fold differently or not fold at all, becoming useless tangles of atoms. DNA, the molecule that stores genetic information, depends on precise base pairing between complementary strands. Adenine bonds with thymine, guanine with cytosine, held together by hydrogen bonds of very specific strengths. Change these bond strengths, and DNA might not be stable enough to store information reliably, or might be so stable that it can't be copied and transcribed when needed. But chemistry isn't just about individual molecules, it's also about reactions, the processes by which molecules break apart and recombine to form new substances. Every reaction has an energy barrier, an amount of energy needed to get it started. This barrier height depends on the electromagnetic forces we're altering. Some reactions that are easy in our universe might become difficult or impossible. Others that are currently impossible might become spontaneous. The entire landscape of chemical possibility would shift, creating new pathways for molecules to form and transform. Catalysis, the process by which certain substances speed up chemical reactions without being consumed, would also be affected. Catalysts work by providing alternative reaction pathways with lower energy barriers. Change the electromagnetic forces, and you change these energy landscapes, potentially making current catalysts ineffective while creating opportunities for new ones. This has profound implications for biochemistry. Living systems depend on enzymes, biological catalysts that speed up the chemical reactions necessary for life. These enzymes are precisely shaped proteins that lower the energy barriers for specific reactions, making life's chemistry fast enough and efficient enough to sustain complex organisms. In our altered universe, current enzymes might not work properly. The reactions they catalyze might require different activation energies, or the enzymes themselves might not fold into the right shapes to provide catalysis. Life might need to evolve completely different enzymes, or might not be able to achieve the chemical complexity necessary for biology at all. Even simple combustion would be affected. Fire is a chemical reaction between oxygen and fuel that releases energy. Change the electromagnetic forces governing this reaction, and you change how easily things burn, how much energy is released, how fast the reaction proceeds. Maybe wood wouldn't burn at all in our new universe, making fire impossible and fundamentally altering the development of technology and civilization. Maybe everything would burn more easily, making the world a much more dangerous place. Maybe combustion would release different amounts of energy, changing the entire energy economy of both biology and technology. The atmosphere itself would be different. The molecules that make up air, nitrogen, oxygen, carbon dioxide, water vapor, all would behave differently. Maybe oxygen would be less reactive, making breathing less efficient. Maybe nitrogen would be more willing to form compounds, changing soil chemistry and plant nutrition. Photosynthesis, the process that converts carbon dioxide and water into sugar using sunlight, might not work at all. This reaction depends on precisely tuned molecular machinery that captures light energy and uses it to drive chemical reactions. Change the chemical rules, and this machinery might not function, eliminating the primary source of energy for most life on Earth. So in our slower light universe, chemistry would be recognizable but transformed. Familiar molecules would have unfamiliar properties. New kinds of molecules might be possible while old ones become unstable. The entire molecular foundation of existence would be rebuilt according to different rules. It would still be chemistry, still the dance of atoms forming and breaking bonds, still the endless creativity of matter organizing itself into complex structures. But it would be a different dance, with different steps, different rhythms, different possibilities for beauty and complexity. Life, it seems, is surprisingly particular about the universe it chooses to inhabit, rather like a very picky house guest who needs everything just so. Temperature has to be just right, not too hot, not too cold. Chemistry has to be just complex enough to allow for interesting molecules, but not so chaotic that nothing stable can form. Energy sources need to be abundant but not overwhelming. And the fundamental constants that govern physics need to fall within a very narrow range that permits the delicate dance of biochemistry. So what happens to life when we slow down light by 10%? Would biology find a way to adapt to the new rules? Or would the changes be too dramatic for life as we know it to exist at all? Let's start with the most basic requirement: energy. All life depends on capturing and using energy from the environment. Plants capture sunlight through photosynthesis. Animals eat plants or other animals. Bacteria might use chemical energy from sulfur compounds or methane, but every living thing needs some source of energy to power the chemical reactions that keep it alive. In our slower light universe, the energy landscape would be fundamentally different. Sunlight would carry different amounts of energy per photon. Chemical reactions would have different energy requirements. The entire energy economy of life would need to be restructured. Photosynthesis might be the most affected process. Plants capture specific wavelengths of light using chlorophyll and other pigments, molecules that are precisely tuned to absorb light of particular energies. The energy from these photons drives the chemical reactions that convert carbon dioxide and water into sugar. But in our altered universe, light would have different energies, atoms would have different energy levels, and chemical reactions would have different requirements. The chlorophyll that works so well in our universe might be completely useless, unable to capture the right wavelengths or provide the right amount of energy for photosynthesis. Plants might need to evolve entirely different pigments, molecules that could harvest the altered solar spectrum efficiently. Maybe they would be purple instead of green, or black to absorb a broader range of wavelengths, or transparent to let light pass through to multiple layers of photosynthetic machinery. Or maybe photosynthesis wouldn't work at all. Maybe the energy available from sunlight in our slower light universe wouldn't be sufficient to drive the complex chemistry of sugar production. Life might need to rely entirely on chemical energy sources, breaking down minerals or organic compounds instead of harvesting solar energy. This would fundamentally change ecosystems. Without photosynthesis, there would be no primary producers, no organisms capable of converting inorganic materials into the organic molecules that feed food webs. Life might be restricted to environments rich in chemical energy, like deep-sea hydrothermal vents or underground communities that feed on radioactive decay. But let's assume life found a way to capture energy in this new universe. The next challenge would be the chemistry of life itself. Every living thing is essentially a collection of chemical reactions, thousands of them happening simultaneously in precise coordination. These reactions depend on enzymes, protein molecules that act as biological catalysts, speeding up specific chemical transformations. Enzymes work by precisely positioning reactant molecules and lowering the energy barriers for reactions. They're like molecular matchmakers, bringing the right chemicals together under the right conditions to make biology possible. In our altered universe, the electromagnetic forces that govern enzyme function would be different. Proteins might fold into different shapes or not fold properly at all. The energy barriers for biochemical reactions would shift, potentially making current enzymes ineffective. Life might need to evolve entirely new enzymes, proteins with different shapes and different catalytic abilities suited to the new chemical landscape. This wouldn't necessarily be impossible, but it would be a massive undertaking, requiring the evolution of new protein families, new metabolic pathways, new biochemical networks. DNA itself might be problematic. The double helix structure of DNA depends on hydrogen bonds between complementary base pairs, bonds of very specific strengths. Change the electromagnetic forces, and these bonds might be too weak to hold DNA together reliably, or too strong to allow the molecule to be copied and transcribed when needed. Maybe life would need to use a different information storage molecule, something more stable or more flexible than DNA. RNA, proteins, or entirely novel molecular systems might serve as the basis for heredity and evolution. Cell membranes present another challenge. These thin barriers that separate the inside of cells from the outside world are made of lipid molecules that organize themselves into double layers. This organization depends on the balance between hydrophobic and hydrophilic forces, attractions and repulsions that might be different in our altered universe. Maybe cell membranes would be more permeable, allowing substances to pass through more easily. Maybe they would be less permeable, making it harder for cells to exchange materials with their environment. Maybe the current membrane chemistry wouldn't work at all, requiring life to evolve entirely different ways of maintaining cellular integrity. But life is remarkably adaptable. Over billions of years, it has colonized almost every environment on Earth, from scorching hot springs to frozen Antarctic valleys, from acidic volcanic pools to highly radioactive zones. Life finds a way to extract energy, build complex molecules, and reproduce even under conditions that seem impossible. Maybe life in our slower light universe would be just as creative. Maybe it would find new ways to capture energy, new types of biochemistry, new solutions to the challenges of existence. The resulting organisms might be utterly alien to us, based on different chemistry, using different energy sources, but still recognizably alive. Perhaps they would be larger, taking advantage of different optimal sizes for biochemical processes. Perhaps they would be smaller, finding efficiency in miniaturization. Perhaps they would be more communal, forming collective organisms where individual cells specialized in different aspects of the altered biochemistry. The timescales of life might be different too. If chemical reactions proceeded more slowly, life processes might be slower, leading to organisms that lived longer, reproduced less frequently, evolved more gradually. Alternatively, if some reactions became more efficient, life might speed up, becoming more dynamic and short-lived. Intelligence, if it evolved at all, might take different forms. Brains depend on electrical and chemical signaling between neurons, processes that would be affected by changes in electromagnetic forces. Maybe intelligence would be based on different physical processes, or maybe conscious thought would operate on different timescales. There's also the question of whether complex multicellular life could evolve at all. The transition from simple single-celled organisms to complex multicellular ones required the evolution of sophisticated cellular cooperation, communication, and specialization. This transition might be easier or harder in our altered universe, depending on how the changes affected cellular biochemistry. Maybe life would remain simple, stuck at the level of bacteria and other microorganisms. Maybe it would develop complexity along completely different lines, creating forms of organization and intelligence that we can barely imagine. Or maybe, despite life's remarkable adaptability, the changes would be too severe. Maybe the window of physical conditions that allows for the emergence and sustenance of life is narrower than we realize. Maybe slowing light by just 10% would be enough to close that window, leaving our universe beautiful and complex but eternally lifeless. The only way to know for sure would be to wait and see what emerged from billions of years of chemistry and evolution in this strange new cosmos. But one thing seems certain: if life did find a way to exist in our slower light universe, it would be wonderfully, beautifully, completely different from anything we know. Every device around you, from the phone in your pocket to the microwave humming in your kitchen, depends on electromagnetic waves behaving in very specific, predictable ways. But in our 10% slower universe, these electromagnetic behaviors would be fundamentally different. The technology that defines our modern world would either need to be completely reimagined or might not work at all. From the simplest light bulb to the most sophisticated computer, everything would need to adapt to new electromagnetic realities. Let's start with something basic: electric lights. When you flip a switch, electricity flows through a wire and into a bulb, where it encounters resistance. This resistance converts electrical energy into heat and light, making the filament glow. Simple enough. But the wavelengths and energies of that light would be different in our slower light universe. The filament might glow redder or require different temperatures to produce useful illumination. LED lights, which work by exciting electrons in semiconductor materials, would emit completely different colors as the electronic energy levels shifted. Maybe the warm white light we're accustomed to would be impossible to produce efficiently. Maybe all artificial lighting would have a distinctly different character, redder or bluer, or some color that doesn't exist in our current spectrum. This might seem like a minor inconvenience, but consider how much our technology depends on precise control of light wavelengths. Fiber optic communications, the backbone of our internet, rely on light pulses traveling through glass fibers. These systems are precisely tuned to specific wavelengths that propagate efficiently through the fiber material. Change the electromagnetic spectrum and you might need entirely different wavelengths, different fiber materials, different optical components. The slower speed of light would also affect signal propagation times. Currently, light travels from New York to London through undersea fiber optic cables in about 28 milliseconds. In our slower universe, this delay would increase to about 31 milliseconds. That might not sound like much, but it would affect high-frequency trading, real-time communications, and any application that depends on precise timing. Radio communications would face even bigger challenges. Radio waves are just low-frequency electromagnetic radiation, and they would be affected by all the same changes we've been discussing. Radio transmitters and receivers are precisely tuned to specific frequencies using antennas designed for particular wavelengths. In our altered universe, the relationship between frequency and wavelength would be different. Current radio equipment might not work at all, transmitting at the wrong frequencies for efficient propagation, using antennas of the wrong size to couple effectively with the electromagnetic field. Cell phones, Wi-Fi, GPS, all of these technologies would need to be redesigned from the ground up. Maybe they would operate at completely different frequencies, require different antenna designs, use different modulation schemes. Maybe some of them wouldn't be practical at all if the altered electromagnetic properties made radio propagation less efficient. GPS faces a particularly interesting challenge because it depends not just on radio communications, but also on extremely precise timing. GPS satellites carry atomic clocks and constantly broadcast time signals. Your phone determines its location by measuring tiny differences in the arrival times of signals from multiple satellites. But we've already seen that time itself would behave differently in our slower light universe. The relativistic effects that GPS systems must account for would be altered. The relationship between time, space, and gravity would follow new rules. GPS might need completely different mathematical models to maintain its precision, or might not be accurate enough to be useful. Computers present their own challenges. Modern electronics depend on the behavior of electrons in semiconductor materials like silicon. These behaviors are governed by quantum mechanics and electromagnetic forces, both of which would be affected by our fundamental constant changes. The band gaps in semiconductors, the energy differences that determine whether materials conduct electricity or act as insulators, would shift. Silicon might no longer be the ideal material for computer chips. We might need to use different semiconductors or entirely different technologies for information processing. The speeds at which electronic signals propagate through computer circuits would also change. While these speeds are much slower than light speed, they're still related to electromagnetic properties that would be altered. Computer processors might need to run at different clock speeds or use different architectures to achieve the same performance. Microwave ovens, those convenient appliances that heat food by exciting water molecules with electromagnetic radiation, would probably not work at all. They're precisely tuned to a frequency that efficiently couples with water molecules. Change the electromagnetic spectrum, and this frequency might not exist, or might not be practical to generate. Maybe food heating would require entirely different technologies, or maybe we'd discover that some other frequency in the altered spectrum worked even better than our current microwave technology. Solar panels face the same challenges as biological photosynthesis. They're designed to convert specific wavelengths of sunlight into electrical energy, using materials with precisely tuned electronic properties. In our slower light universe, sunlight would have different wavelengths and energies, potentially making current solar technology completely ineffective. Maybe we'd need to develop solar panels using different materials, designed for different parts of the altered electromagnetic spectrum. Maybe solar energy would be less practical, forcing us to rely more heavily on other energy sources. Maybe, in some lucky twist, the changes would make solar energy more efficient rather than less. Medical imaging technologies like X-rays, MRI, and CT scans would all be affected. These depend on electromagnetic radiation interacting with human tissue in specific ways. X-rays work because they have just the right energy to penetrate soft tissue while being absorbed by bones. Change the electromagnetic spectrum, and this might not be possible with any available wavelength. MRI uses powerful magnetic fields and radio waves to make hydrogen atoms in your body emit signals that can be detected and used to create images. The specific frequencies used are related to fundamental atomic properties that would shift in our altered universe. Maybe medical imaging would require completely different technologies, or maybe some imaging techniques would become easier while others became impossible. Maybe we'd develop entirely new ways of seeing inside the human body based on the altered electromagnetic realities. Even something as simple as photography would be transformed. Cameras detect light using materials that are sensitive to specific wavelengths. Digital sensors, photographic film, and the human eye itself are all tuned to the electromagnetic spectrum as it exists in our universe. In the slower light cosmos, we might need different sensor materials, different film chemistry, or might discover that some previously invisible part of the spectrum becomes the new visible light for imaging purposes. The laser technology that powers everything from barcode scanners to precision manufacturing would need to be reimagined. Lasers work by exciting atoms to emit light of very specific wavelengths. Change the atomic energy levels, and you change what wavelengths are available for laser operation. Maybe some laser applications would become impossible, while others that are currently impractical would become easy. Maybe holography, precision measurement, laser surgery, and industrial cutting would all need to adapt to new wavelengths and new physical possibilities. But here's the remarkable thing about human ingenuity. We're incredibly good at working with whatever universe we find ourselves in. If we had evolved in a slower light cosmos, our technology would have developed along completely different lines, but it might be just as sophisticated and useful. We might have radio communications at different frequencies, computers based on different physical principles, energy systems that harvest different parts of the electromagnetic spectrum. Our technology would be alien to us, but it might be just as capable of connecting us, empowering us, and expanding our understanding of the cosmos. The universe sets the rules, but human creativity finds ways to play the game. Vision, as it turns out, is just your brain's interpretation of electromagnetic waves bouncing off the world, and like any good interpreter, it's doing quite a bit of creative translation. Let yourself imagine waking up in our slower light universe. Don't worry about the complex physics, just feel what it might be like to open your eyes to a world painted in completely different hues. The morning light filtering through your window might feel thicker somehow, more golden, like honey poured through glass. Colors that have no names in our language might dance across familiar objects, making your bedroom feel both cozy and wonderfully strange. Your eyes, if they had evolved in this universe, might see heat the way you currently see color. Imagine looking at a warm cup of tea and seeing not just its ceramic surface, but the gentle glow of warmth radiating from it like a soft aura. Your lover's skin might shimmer with the faint heat of life, visible as clearly as their smile. The world would be painted not just in light, but in the gentle signatures of warmth and coolness, creating a richer, more intimate visual experience. Perhaps the night sky would reveal secrets currently hidden from human eyes. Stars might appear to pulse with different rhythms, their surfaces painted in wavelengths that tell stories about their age and composition. Flowers might display intricate patterns, invisible to our current vision, but blazing with meaning for eyes, evolved to see this altered spectrum. Don't strain to understand the details. Just drift through this imagined world where seeing itself has been transformed. The quality of light might feel different against your skin too. Sunlight, filtered through this slower electromagnetic reality, might feel gentler, more caressing. Perhaps you could spend longer hours outdoors without the harsh intensity we sometimes experience, as if the universe had learned to touch you more softly. Shadows might be deeper and more welcoming, offering a different kind of rest, a different rhythm to the day. Sleep itself might come differently in such a world. If the light that regulates your internal clock carried different energies, different messages to your brain, your circadian rhythms might flow like a slower river. Perhaps you'd wake more gradually, with the natural world's altered sunrise painting your consciousness in gentler hues. Perhaps rest would come more easily, as if the very light around you was designed for deeper peace. Let your imagination rest in this altered world for a moment. Feel the weight of different air, breathe in light that carries unfamiliar energies, exist for a while in a universe that chose to see beauty through a different lens. There's something quietly profound about realizing that consciousness itself might paint reality in completely different colors, yet still find it beautiful, still call it home. your emotional relationship with light might be transformed too. The warm golds and deep roses of this imagined sunlight might evoke feelings that have no names in our current language. Maybe you'd find peace in wavelengths that currently seem empty and dark. Maybe the night would feel less like absence and more like the presence of different kinds of illumination, invisible to us but deeply felt by minds that evolved to appreciate this gentler spectrum. Don't try to hold on to all the technical details about how vision works or why electromagnetic spectra shift. Just rest in the wonder of imagining consciousness painting reality in entirely different hues, yet still finding beauty, still feeling at home, still watching sunsets with the same sense of peace and gratitude. Even if those sunsets glow in colors that don't exist in the world outside your window. But vision is more than just detecting light. It's about processing that information, interpreting patterns, recognizing objects, navigating through space. Your brain has evolved sophisticated neural networks to make sense of visual information, networks that are tuned to the specific characteristics of light as it exists in our universe. These processing systems might not work optimally with altered electromagnetic input. Maybe depth perception would be more difficult if the wavelengths needed for effective stereoscopic vision weren't available. Maybe motion detection would be impaired if objects didn't reflect light in familiar ways. Maybe pattern recognition would be compromised if the contrast and detail information your brain expects wasn't present in the new spectrum. Of course, if humans had evolved in the slower light universe from the beginning, these systems would have developed differently. Your brain would be optimized for processing whatever electromagnetic information was available, creating rich, detailed perceptions from whatever light existed. But that raises a deeper question. Would humans exist at all? The evolution of complex life, including the eventual emergence of human beings, depended on countless environmental factors, from the energy output of the sun to the chemistry of early Earth's atmosphere. Change the electromagnetic spectrum, and you change how photosynthesis works, which affects what kinds of plants can exist, which affects what animals can evolve to eat those plants, which affects the entire evolutionary history that led to human beings. The butterfly effect suggests that even tiny changes early in Earth's history could lead to completely different outcomes. Maybe in our slower light universe, evolution would have taken a completely different path. Maybe intelligence would have evolved in entirely different organisms, creatures that seem alien to us but are perfectly adapted to their electromagnetic environment. Maybe humans would never have existed, replaced by beings whose sensory experiences and cognitive processes we can barely imagine. But let's assume, for the sake of argument, that something recognizably human did evolve. How would daily life be different? The rhythm of day and night might feel different if sunlight had altered intensity or color temperature. Maybe days would feel longer or shorter, not because of actual time differences, but because of how your brain processes the available light. Sleep patterns might be affected too. Human circadian rhythms are partly regulated by light exposure, particularly blue light that signals daytime to your internal clock. If the electromagnetic spectrum shifted, these regulatory mechanisms might not work properly, leading to sleep disorders, mood changes, or completely different daily cycles. Artificial lighting would pose its own challenges. The incandescent and LED bulbs that currently illuminate your home might produce light that seems dim, harsh, or uselessly colored in the new electromagnetic landscape. Maybe effective artificial lighting would require entirely different technologies, creating indoor environments that feel alien compared to what you're used to. Your skin would respond differently to sunlight too. Currently, ultraviolet radiation can cause sunburn and skin damage, while also triggering vitamin D production. In our altered universe, different wavelengths might be harmful or beneficial, or completely irrelevant to human physiology. Maybe you'd need to worry about infrared burns instead of ultraviolet damage. Maybe vitamin D production would require exposure to completely different wavelengths, changing how much time you need to spend outdoors and what kinds of protection you need from the sun. Photography and visual art would be completely transformed. The cameras and displays that currently capture and reproduce images are designed for our specific electromagnetic spectrum. In the slower light universe, these might produce images that seem wrong, distorted, or meaningless. Maybe visual art would develop along entirely different lines, using wavelengths and effects that don't exist in our universe. Maybe there would be forms of beauty and aesthetic experience that you can't imagine because they depend on electromagnetic phenomena that aren't available to human perception. Even your emotional responses to light might be different. Humans have strong psychological associations with certain colors and lighting conditions. Red feels warm and energetic, blue feels cool and calm, golden hour light feels romantic and peaceful. These associations are partly learned, but they're also partly biological, based on how your brain processes specific wavelengths. In a universe where these wavelengths don't exist, or carry different energies, or create different physiological responses, your emotional relationship with light and color would be completely different. Maybe you'd find beauty in wavelengths that currently seem invisible and meaningless. Communication itself might be affected. Human language has countless words for colors, for lighting conditions, for visual experiences. Poetry and literature are filled with visual metaphors that depend on shared experiences of light and color. In our altered universe, this entire vocabulary might be meaningless, replaced by words and concepts that describe electromagnetic experiences you can't imagine. But perhaps most remarkably, you might not experience any of these changes as losses or problems. If you had evolved in the slower light universe, your sensory experiences would seem perfectly normal and rich and beautiful. You might look at our universe and think how limited and impoverished our electromagnetic spectrum seems, how much beauty and information we're missing. The universe provides the canvas, but consciousness paints the picture. Whatever electromagnetic realities existed, human awareness would find ways to make them meaningful, beautiful, and deeply felt. The colors might be different, the light might behave strangely, but the human capacity for wonder and perception would remain. And perhaps that's the most remarkable thing of all. Not how much would change, but how much would stay fundamentally the same. Every conversation you've ever had is really just information traveling from one place to another, whether it's sound waves through air or light signals through fiber optic cables. But in our 10% slower universe, this fundamental flow of information would face new obstacles. Messages would take longer to travel, signals would arrive with different timing, and the very infrastructure of communication would need to be rebuilt from the ground up. From texting a friend across town to listening for signals from alien civilizations, everything would change. Let's start close to home. When you make a phone call today, your voice gets converted into electrical signals that travel through wires or radio waves. These signals move at speeds related to the speed of light, though usually somewhat slower depending on the medium they're traveling through. In our slower light universe, these signals would propagate more slowly. A phone call from New York to Los Angeles, which currently involves delays too small to notice, might have a perceptible lag. Not dramatic, maybe just a fraction of a second, but enough to make conversations feel slightly awkward, like talking to someone on a bad video call. Internet communications would be more severely affected. The global network of fiber optic cables that carries internet traffic depends on light pulses traveling through glass fibers. With light moving 10% slower, web pages would load more slowly, video calls would have more lag, and real-time applications like online gaming would become noticeably less responsive. But the real challenges would emerge when we try to communicate across larger distances. Currently, a radio signal takes about 1.33 seconds to travel from Earth to the Moon. In our slower universe, this would increase to about 1.5 seconds. Not a huge difference for casual conversation, but significant for activities that require precise timing and coordination. Mission control talking to astronauts on the Moon would experience longer delays in their conversations. Houston, we have a problem, would arrive in Houston a bit later, and Houston's response would take a bit longer to get back to the Moon. This might not sound like much, but in emergency situations, every second can be crucial. Mars communications would face even bigger challenges. Currently, when Earth and Mars are at their closest approach, radio signals take about 4 minutes to travel between the planets. At their farthest separation, the delay is about 24 minutes. In our slower light universe, these delays would increase to about 4.5 minutes and 26.5 minutes respectively. This would make real-time conversation with Mars colonists essentially impossible. Every question would require at least 9 minutes for a round-trip response at best, and nearly an hour at worst. Mission planning, emergency response, and simple human conversation would all need to account for these extended delays. But perhaps the most profound changes would be in our search for extraterrestrial intelligence. Currently, radio astronomers scan the skies looking for artificial signals that might indicate the presence of alien civilizations. These searches depend on detecting radio waves that have traveled across interstellar distances. With light moving more slowly, these signals would take longer to cross the galaxy. A message from a civilization 1,000 light-years away would take 1,000 years to reach us in our current universe. In the slower light cosmos, the same message would take about 1,100 years to arrive. This might not seem like a big difference, but it would affect the entire timeline of galactic communication. Civilizations would need to be stable for longer periods to maintain meaningful dialogue across interstellar distances. The window of time during which two civilizations could communicate would be shifted, potentially making contact even more rare and precious. The search strategies would need to change too. Radio astronomers currently look for signals at specific frequencies that seem optimal for interstellar communication. But in our altered electromagnetic spectrum, these optimal frequencies might not exist, or might be in completely different parts of the spectrum. Maybe alien civilizations in our slower light universe would communicate using wavelengths that we currently consider infrared or ultraviolet. Maybe they would use entirely different technologies, quantum entanglement or gravitational waves, or some form of communication that doesn't exist in our current physics. Even more intriguingly, the altered physics might allow for new forms of communication that are impossible in our universe. Maybe the changed relationship between space, time, and electromagnetic fields would open up communication channels that don't exist under our current physical laws. But let's think about navigation and timing systems like GPS. These systems work by measuring tiny differences in the arrival times of signals from multiple satellites. The precision required is extraordinary, accurate to billionths of a second, because the satellites are moving and both special and general relativistic effects must be accounted for. In our slower light universe, all of these timing calculations would be different. The relativistic effects would follow altered equations, the signal propagation times would be longer, and the entire mathematical framework for precision positioning would need to be redeveloped. Maybe GPS would be less accurate, making navigation more challenging. Maybe it would require more satellites or different orbital configurations to achieve the same precision. Maybe entirely different technologies would be needed for accurate positioning. The global financial system would face interesting challenges too. High-frequency trading, where computers buy and sell stocks in microseconds, depends on extremely fast communication between trading centers. Even tiny delays can cost millions of dollars when computers are trying to exploit brief price differences between markets. With slower signal propagation, these trading algorithms would need to account for longer delays between markets. Maybe high-frequency trading would be less profitable or would operate on slightly longer timescales. Maybe the entire structure of global financial markets would evolve differently to accommodate the altered communication realities. Emergency services would also be affected. When you call 911, your location is determined partly by measuring the time it takes signals to travel from your phone to cell towers. With slower signal speeds, these calculations would be less precise, potentially making it harder for emergency responders to find you quickly. But perhaps most poetically, the very concept of simultaneous events would be different. In our current universe, Einstein taught us that simultaneity is relative, depending on your frame of reference. Events that appear simultaneous to one observer might not be simultaneous to another observer moving at a different speed. This relativity of simultaneity depends critically on the speed of light. Change that speed, and you change how simultaneity works throughout the universe. Maybe events that seem to happen at the same time would be more obviously separated in time. Maybe the universe would feel more sequential, less parallel. Communication across the cosmos would still be possible, but it would require more patience. Messages would take longer to travel, conversations would have longer pauses, and the entire rhythm of information exchange would be more leisurely. Maybe this would actually be beneficial. Maybe the forced delays would encourage more thoughtful communication, more careful consideration of messages before sending them. Maybe civilizations would become better at asynchronous communication, more patient with long-term projects, more accepting of the time it takes for ideas to propagate across space. In our slower light universe, communication would still connect minds across the cosmos, but it would do so at a more contemplative pace. Information would still flow, but like a gentle stream rather than a rushing river. And perhaps in that slower flow there would be time for deeper reflection, more careful thought, more meaningful exchange of ideas across the vast distances that separate thinking beings in the universe. After all, the best conversations often happen not when we speak quickly, but when we take time to really listen. Cosmology is the art of asking very big questions about very distant things, and hoping the universe is patient enough to provide some answers. In our 10% slower light universe, those answers would be written in a different cosmic script. The entire story of the universe, from its fiery birth in the Big Bang to its ultimate fate trillions of years in the future, would unfold according to different rules, different timescales, different possibilities for complexity and beauty. Let's begin at the very beginning. The Big Bang itself, that moment when space and time and matter burst into existence from an infinitesimal point, would proceed differently. The fundamental equations that govern cosmic expansion depend on the speed of light, and changing that speed would alter the entire early history of the universe. In the first fraction of a second after the Big Bang, the universe underwent a period of rapid expansion called inflation, growing faster than light could travel and smoothing out irregularities that might have prevented the formation of galaxies and stars. With a different light speed, this inflationary period might last longer or shorter, or proceed at a different rate, fundamentally changing the large-scale structure of the cosmos. The cosmic microwave background, that faint afterglow of the Big Bang that still fills all of space, would be different too. This radiation was emitted when the universe first became transparent to light, about 380,000 years after the Big Bang. In our slower light universe, this moment might come at a different time, under different conditions, creating a background radiation with different properties. The tiny fluctuations in this background radiation, the seeds that eventually grew into galaxies and galaxy clusters, might be more pronounced or less pronounced, creating a universe with a different distribution of matter on the largest scales. Maybe our cosmos would be filled with enormous galaxy superclusters separated by vast empty voids. Maybe galaxies would be smaller and more numerous, scattered more evenly throughout space. Galaxy formation itself would follow a different timeline. Currently, the first stars formed when the universe was only a few 100 million years old, just a tiny fraction of its current age. These early stars were massive, short-lived giants that forged the first heavy elements and ended their lives in spectacular supernovae. In our slower light universe, this stellar timeline might be accelerated or delayed. Maybe the first stars would form earlier, when the universe was denser and hotter. Maybe they would form later, after more time had passed for matter to cool and collect. Maybe they would be fundamentally different, massive or small, bright or dim, depending on how the altered physics affected stellar formation and evolution. The elements created by these early stars would be different too. We've already seen how nuclear fusion would proceed differently with altered energy relationships. Maybe our slower light universe would be richer in some elements and poorer in others, creating a different palette for cosmic chemistry. This would affect planet formation in profound ways. Rocky planets like Earth depend on the availability of heavy elements like silicon, iron, and magnesium. Gas giants need hydrogen and helium, but also heavier elements to form their solid cores. Change the cosmic abundance of these elements, and you change what kinds of planets can form, where they can form, and how common they might be. Maybe our slower light universe would be filled with gas giants, but lacking in rocky worlds. Maybe the reverse would be true, with abundant terrestrial planets, but few gas giants. Maybe entirely new types of planets would be possible, made from combinations of elements that are rare in our current cosmos. The habitable zones around stars, those regions where liquid water can exist on planetary surfaces, would shift too. With stars burning differently, these zones might be closer to their stars or farther away, narrower or wider, more stable or more variable over time. But let's think even bigger about the ultimate fate of the universe itself. Currently, our cosmos appears to be expanding faster and faster, driven by a mysterious force called dark energy. This expansion will eventually spread galaxies so far apart that they can no longer interact. Stars will burn out, black holes will evaporate, and the universe will end in a cold, dark, empty state, sometimes called the heat death. But this fate depends on the precise balance between different forms of energy and matter in the universe, including the energy stored in electromagnetic fields. Change the speed of light, and you might change this balance, leading to a completely different cosmic destiny. Maybe our slower light universe would expand more slowly, giving gravity more time to pull things back together, eventually leading to a big crunch where everything collapses back into a single point. Maybe it would expand faster, reaching heat death more quickly. Maybe the balance would be so different that the universe would oscillate, expanding and contracting in endless cycles. The formation and behavior of black holes would be affected too. These extreme objects, where gravity is so strong that not even light can escape, would still exist in our altered cosmos, but they might form under different conditions and behave in subtly different ways. Black hole evaporation, the slow process by which black holes lose mass by emitting Hawking radiation, depends on quantum mechanical processes that would be altered by changes in fundamental constants. Maybe black holes would evaporate faster or slower, changing how long they persist and how they affect their surroundings. galaxy collisions, those majestic cosmic events where entire star systems merge over hundreds of millions of years, would also evolve differently. The gravitational waves produced by these mergers travel at the speed of light, so they would propagate more slowly through our altered space-time, carrying information about cosmic events at a more leisurely pace. Even the expansion of space itself might feel different. Currently, distant galaxies appear to be moving away from us faster than nearby ones, and the most distant galaxies we can observe appear to be receding at significant fractions of light speed. In our slower light universe, these recession velocities would have different relationships to the underlying expansion of space. Maybe we could see farther into the cosmic past, or maybe our view would be more limited. Maybe the observable universe would be larger or smaller, changing how much of cosmic history we could study and understand. Dark matter and dark energy, those mysterious components that make up most of the universe's mass and energy, might behave differently too. While we don't fully understand these phenomena even in our current universe, they likely depend on fundamental physics that would be altered by changing the speed of light. Maybe dark matter would clump differently, affecting how galaxies form and evolve. Maybe dark energy would be stronger or weaker, changing the expansion rate of the universe. Maybe these mysterious components would reveal themselves more clearly in our altered cosmos, or maybe they would become even more hidden and puzzling. The universe would still be vast, still be ancient, still be filled with wonders beyond imagination. Stars would still shine, planets would still orbit, galaxies would still spiral through the cosmic dance. But it would all happen according to different rules, creating different patterns of beauty and complexity. Maybe our slower light cosmos would be more conducive to life, with more stable stars, more habitable planets, more time for complex chemistry to develop. Maybe it would be less hospitable, too harsh, or too gentle for interesting phenomena to emerge. Maybe it would simply be different, filled with forms of beauty and complexity that we can't imagine because they don't exist under our current physical laws. In the end, the universe would still be the universe, magnificent, mysterious, and endlessly creative. It would still find ways to organize matter and energy into intricate patterns, still create conditions where complexity can emerge, still produce phenomena that inspire wonder and curiosity. The speed of light sets the tempo for this cosmic symphony, but the music would be beautiful regardless of whether it played at our familiar pace or at the more contemplative rhythm of our imagined slower universe. And so, we float gently back to our own universe, where light races along at its familiar breakneck pace of 299,792,458 meters per second. What a strange and wonderful journey we've taken together, wandering through a cosmos where light decided to slow down just a little. We've seen atoms dance to different rhythms, stars sing altered songs, and time itself flow according to new rules. We've imagined technology that doesn't exist, chemistry that follows different patterns, and life that might evolve along completely alien pathways. But perhaps the most remarkable discovery from our thought experiment is just how delicately balanced our own universe really is. Every fundamental constant, every physical law, every cosmic parameter seems to be set just right for the emergence of complexity, beauty, and eventually, consciousness itself. The speed of light isn't just a number. It's one thread in an intricate tapestry that weaves together space and time, matter and energy, cause and effect. Pull on that thread, even gently, and the entire pattern shifts, creating new possibilities while foreclosing others. We live in a universe where stars burn at just the right rate to create the elements of life, where atoms form bonds strong enough to build complex molecules, but flexible enough to change and adapt. where electromagnetic radiation carries just the right amount of energy to power photosynthesis and allow us to see the beauty around us. Tonight, as you settle into sleep, perhaps you'll carry with you a deeper appreciation for the cosmic conditions that make your existence possible. Every breath you take, every thought you think, every moment of wonder you experience exists because this universe happens to have exactly the right speed limit for light. Sweet dreams, fellow traveler. Thanks for joining us here at Sleep Science.